the top as a trinomial and the bottom already in factored form. And it's already compared to 0. Okay, so what we got to do here is see if we can factor the numerator, which we can because I made this up. Sometimes you can't, and we'll look and see how to deal with that issue, which might crop up. I like to be thorough. So let's see if we can factor this. And again, we can. So 2 times -6 factors in -12 that add to be -1, and that would be -4 and 3. Yeah, okay, so then this becomes on top 2x times x. And so I'm thinking the 2 times -2 would get the -4x, and then the 3 times x would get that. All right, so inner outer terms, reverse FOIL factoring. All right, so now we got this. Now there's 2 cases here. Keep in mind that where this comes from, right? If we have a graph of these things, you know, we have some vertical asymptotes, and we also have x-intercepts. So with the x-intercepts, that's one point where we're going to be either above or below the x-axis, right? And so depending on the nature of the graph, so the location of the x-intercepts we got to find. Also the location of the vertical asymptotes, because in between the graph will either be above if there's no x-intercepts in the middle, or below. So when we use test points, we not only want to find the x-intercepts, which is coming from the numerator, but we also want to find the vertical asymptotes, which is coming from the denominator. And those are going to mark off the regions. Because we might have an x-intercept in the middle here. So then we would have a region between the vertical and the x-intercept on either side of this. Okay, so it's no different than what we just did. It's just we got to get not just the x-intercepts, we got to get the vertical asymptotes. So I call them numerator zeros, denominator zeros. Okay, so numerator zeros, you solve equal to 0, -3/2 and 2. Denominators equal zeros, those are the vertical asymptotes. You solve equal to 0, you got 1 and -2. Now there is a multiplicity that's even here. And so you can use that to your advantage if you're good with that, but not necessary if we use test points. Okay? Now the numerator zeros, those are the x-intercepts, and the denominator zeros, those are the vertical asymptotes. So when I do my number line with this, if it's a numerator 0, I put a dot. If it's a denominator 0, I'll put like a little line. And that'll just remind me that that came from a vertical asymptote. All right, so -2, I'm going to put a little line. -3/2, I'm going to put a dot because that came from the x-intercept, numerator 0. 1, I'm going to draw a little line because that came from a vertical asymptote. And 2, I'm going to put a dot. Now, I'm not trying to space this correctly. So I'm not trying to draw this to scale. All right, so notice how many intervals we got to check. Within each of these intervals, the graph is either going to be above or below. And so now we can just use test points. We already have a factored form. On the bottom, we already have something that's always positive. So we got the 3 other factors that could be positive or negative. This one I'm covering up that has an exponent 2 is always going to be positive. Okay, so again, you can pick whatever number you want. So, you know, whatever works for you will be fine. Now, these two are pretty close. So I'm going to use -1.8. All right, and then if you can use a 0, that's almost always a good one to use. And then 1.5. And then just for the sake of it, I'll use 10. Okay, so then you just pop that in here and decide whether you get positive or negative. Okay, so -4, negative, negative, positive, negative. Right, and that's what that is indicating. I'm mapping it to the two terms on top divided by the two terms on bottom. Okay, and then that's negative 1.8. So negative 1.8, definitely make this bigger than negative 3, because it'd have to be negative 1.5 to get to 3. So negative, negative 1.8 negative. This one now becomes positive, and that's always positive. So negative, negative, positive, positive. 0, you're going to get a positive, a negative, and then two positives on the bottom. Okay, and then in between 1 and 2, you're going to get a positive, a negative. So at 1.5, positive, negative, and then two positives on the bottom. Okay, and then 10. And when you put 10 in, they're all positive. All right, and notice the even multiplicity. Notice on either side of the 1, which came from a vertical asymptote, these are both the same. Since that's a vertical asymptote, that means the branches of the graph either go both up or both down. In this case, we're getting two negatives. So the branches of the graph would have gone both down together on either side of that vertical asymptote. So you can sketch the graph this way too. All right. So what are we looking for when this is less than or equal to 0? So we're looking for negatives. Okay, and it's only going to equal at the x-intercepts. So that's why I'd make my little notation with the dots and the little line. Okay, so less than or equal to 0, well, that's right here. That's in this region. And I didn't circle around the 1. So we got to be careful, because we can't equal at 1. And it's really easy to overlook that little subtle thing, right? We're going to have to construct 1, 2, 3 inequality statements. We can't just say in between negative 3 over 2 and 2, because it doesn't equal. So it can't equal. I'm sorry, did I just? Yeah, it doesn't equal from a vertical asymptote. I was about to say something else. All right. So at 1, you get an undefined value. All right. So for this one, less than negative 2. Now again, it can't equal negative 2 because that's vertical asymptote. Between negative 3 over 2 and 1, and it can equal negative 3 over 2. And then between 1 and 2, and it can equal 2. And then you would use the word or.